frequency division multiplexing. This is, it's sort of everybody's popular waveform today. It's what your 802.11a and G are built on top of. The DAB stuff is that way, bunches of them. FSK, GMSK, PSK, QAM. ATSC is the US digital television standard. And we got some stuff coming in the future, kind of depending on people's interest, which is fast frequency hopping, as well as the direct sequence spread spectrum. There's a new extension to GNU Radio that's kind of currently in the alpha testing stage, is this idea for message blocks. We've been at this for several years now, and one of the things we noticed is that the data flow abstraction works really well for some physical layer stuff. But then you have a situation where you have a lot of either control plane information, or you have packet-based data where you really want to attach a set of attributes to a packet. And you say, hey, radio, can you transmit this using a particular modulation scheme or a particular amount of power? Or maybe there's like some annotations, like if you have a steerable antenna, please steer the antenna 100 microseconds prior to transmitting the packet. So we basically have this annotations on the side. Also support for doing really precise timing, which allowed you to do time division, multiple access waveforms, kind of things where you got slotted things, or where there's real tight, you got to do something and get a response back. And it's all going to work with the classic GNU Radio all strung together. I'm going to show you a couple of interesting things. This is kind of crazy things people have done with GNU Radio, and this is my latest favorite, and I thought this is good for this crowd, which is, speaking of drones, this is about a 3-meter wingspan little airplane, kind of like a big model airplane, or looks like a little Cessna 172 that's all shrunk down to about 3 meters across. And what people are doing with this is building a synthetic aperture radar system. So it's an active radar system that can image what it flies over. It flies at about a kilometer high off the ground, and it's the neat part is it's built out of one of these universal software radio peripherals that Matt's going to talk about in a minute. A regular, just low-cost single-board computer, off-the-shelf 3-watt, Wi-Fi amplifier, and they managed to build a whole radar system out of this thing. So it's a lot. This is the $5,000 solution, including, not the $500,000 solution. So, probably more than anybody wants to know, but they're generating the radar chirps in the FPGA and blah, 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 blah. They come out, and then it listens, and it comes back, and it basically, there's just generating the chirps and storing them in the little airplane, and when the airplane gets back, they suck the data out of it, and then they do a lot of math to put this thing together. The other thing is they're flying this airplane in circles, which is not the usual straight across. And then the math is like for CAT scans or tomography, where you've got this redundant data because the airplane's flying in a circle. Anyway, neat stuff. Some direction on kind of where we're headed in the future here is that Moore's law has continuing. I mean, Moore's law is what made software radio possible. Like 10 years ago, people would say software radio. You say, yeah, right. How are you going to do that? 5 years ago, it started to become possible. Now it's getting insanely interesting, in that we've got you've got the multi-core. All of a sudden, you can buy your quad-core Xeons. Or you got the Berkeley people who are saying, well, what we really need to do is start designing for 1,000 processor systems. Because your whole software paradigm is going to change. Like you can kind of go to 4 to 8 to 16, but then what about 1,000? They want to do that because they believe they can make that hardware to continue to scale for performance, but it's got to be lots of parallelism. Other thing is you got your clusters or multi-computers, and also then we've got these heterogeneous machines arising. The current one that kind of is popular is the Cell broadband engine, which has a PowerPC core on it and then 8 of these synergistic processing units, which are basically these SIMD. They basically do really fast floating point arithmetic. More on that in a minute. And another sort of a thing got my eye on here is when we start looking at all these different platforms for doing the signal processing, you've got the general purpose processor, things like the cell, which I'll show you in a minute, the graphics processors, and then the FPGA. And right now, when you write the code, they're really written in different styles. Some of them, they're in different languages. They got different set of constraints. And I would like to find some way that you have a high-level way that's implicitly parallel, so we can take advantage of all this parallelism, and it's probably functional. For those of you who aren't familiar with the cell, this is just, you could do like hours on this, but the thing to know is there's this PowerPC over here. It's kind of a very sort of medium lame PowerPC. And then there are 8 of these units that are designed to do single precision floating point really quickly. This is the processor that's in the Sony PlayStation 3, but it's also in these big blade servers that are being built by IBM and by Mercury. There's this big ring that connects everything together, and the ring, you can push about 170 gigabytes per second around that ring. And the memory interface is really quite high. You get like about 24 gigabytes a second to main memory. The thing can do about 200 gigaflops at peak, and we think we can do about 30 gigaflops sustained. So one of these things that's in a Sony PlayStation 3 is about roughly 8 to 10 PCs worth of floating point performance. And that's what pretty much all we do in software radio. So we're really excited about this. So pretty much when I get back to the States, then I start working on this stuff. This is about resources. So I'm going to hand off now to Matt. We'll do some Actually, is there any questions right now? We'll do more Q&A at the end, but before I step down, any questions so far? All right, good. This is Matt. He's going to talk about the Universal Software Radio Peripheral and where that's going. Oh. Please stand by.
I think the mic's a little strong, getting all my breathing.
You just get used to the fact that it's echo, 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 echo.
Okay. Does everybody hear me? That's good. Okay. Okay. So the hard thing with software radio is that you have to get your samples in and out of the computer, and no matter how much you process them in the computer, there's no real place to plug an antenna into it. And so I guess it's about 5 years ago now, I recognized this problem and decided that I wanted to create some open hardware to allow us to really do interesting things with software radio and GNU Radio in particular. And so I went about creating the USRP, or Universal Software Radio Peripheral. And actually at the camp 4 years ago, had the first prototypes of it here, and we're playing around with them, bringing them up. I had just gotten them back. So in any case, the goals for the USRP design were first to be very low cost and to be open, so that we could have a lot of participation, especially in this community, and to share and all learn from it. It was collaboratively developed with input from a large number of people all over the world. And to make it easier to use for a wide-ranging different applications in software radio, we wanted to have interchangeable RF sections that would allow us to plug on different modules for different frequency bands to make it more flexible. And things I was interested in were wide bandwidth and beamforming and MIMO solutions. MIMO is like 802.11n now, is the new 802.11 system that uses multiple antennas to get higher data rates through the same bandwidth. So the USRP as a whole kind of looks like this. You have a computer which connects to the actual USRP system over USB cable, and on the USRP motherboard you have a USB 2 controller chip which talks to an FPGA over a bidirectional bus, and then the FPGA for transmission, we'll send data out to a digital to analog converter, which will then go to the RF section and out to the antenna. And on receive, the antenna comes in, the RF section processes it in analog, and then it's digitized again on the USERP motherboard in the A to D converters and comes back into the FPGA and would go back into the host computer. And in the USERP, there's actually 2 copies of this the RF section, A to D and D to A converter. So one FPGA, but 2 of these other sections. Yes? Is it too loud or too quiet? Yeah, you're getting my breath. Okay. Okay, much better. Thank you. Okay, so what goes on inside the FPGA? We have our bus interface that talks to the USB 2 controller. And that's how we get our samples in and out of the computer. What we usually typically send over the USB bus is raw samples. So on transmit, they would come in and we would go through an interpolator. An interpolator takes a lower sample rate and essentially interpolates the samples in between those so that you can have a higher sample rate. And then it comes out, it is digitally up-converted and sent to the D to A converter. And Cordic and CIC are just efficient algorithms for doing that in an FPGA. On the receive side, we do the same thing. We have a digital down converter, a decimator, and it goes into the bus interface. And then there's control of the whole system. And so that's basically what happens in the FPGA. And this is somewhat out of order. But to tell you what the USERP overall, actually, it would be best if I do the picture first. Okay. This is the USERP. And so the way this works, here's the USB 2 connector that connects to your computer. This is power. This is the USB 2 interface chip. And so this communicates directly with the computer, and it has its own high-speed bus that talks to the FPGA. The FPGA in this case is an Altera Cyclone. And in here we do what I showed on the last slide, which was the digital up and down conversion and the decimation and interpolation, other filtering operations, timing control, that sort of thing. And then these connect to these 2 chips. Now, each of these chips has a dual high-speed A to D and a dual high-speed D to A converter, plus a couple other functions. So this is kind of our analog codec. It takes digital to analog and analog to digital, and there's 2 of them. And each of them, so this one has 2 lines that go to this daughter board connector. This is for the receive side, this is for the transmit side up there, and on this side it's rotationally symmetric. So this is transmit and that's receive up there. And the idea is you would plug on an RF daughter board for your band of interest onto these connectors so that you can basically transmit or receive on your frequencies of interest. So the specs, we have the USB 2 interface, which in theory USB 2 is 480 megabits per second. In practice, we get a nice solid sustained 256 megabits per second, which works out to 32 megabytes per second. And if you're doing, assuming you're doing 8-bit samples, that gives you 32 megasamples per second, which gives you 16 megahertz of RF bandwidth. If you do 16-bit samples, which we typically do, that would give you 8 megahertz of RF bandwidth. So 8 megahertz or 16 megahertz of RF bandwidth in and out of the computer, real-time streaming all day long. We have 4 A to Ds and 4 D to As. The D to As are 128 megasamples, 14 bits, and the A to Ds are half the speed and 12-bit. And so, yeah, in the FPGA, we do these operations, and you can reprogram that. There's nothing non-volatile on the board, so every time you power it up, the host computer loads the FPGA code and the firmware onto the board. So there's no programmer systems you need, and there's no way to wedge the flash in a bad state or anything like that. So it's all sent over, it's bootstrapped over the USB. And you can put 2 TX and 2 RX daughter boards on it at a time. Okay, so daughter boards that are available, there's a whole family of daughter boards. There's the basic TX and basic RX. Those are mostly for experimentation if you have your own external RF section. And they can kind of be an interface to the IF. There's the LFRX and LFTX. This is useful for